So now we will move to the rectangular waveguides, but before that I would like to say a few parting words about the parallel plate waveguide. Okay, the parallel plate waveguide is a very good pedagogical tool, right, in order to show this transverse resonance condition and to give the students a certain feel for how one can arrive at solutions for electromagnetic fields even in bounded situations, right. So I feel like we learned a lot, uh, but in the discussion for parallel plate waveguides I did mention that there can exist a plane wave and grazing incidence launched into the parallel plate waveguide, and this happens only specifically for the TM injection, right. So where the magnetic field is aligned to the y axis and the electric field is in the z axis, right. So if you can recall, that a plane wave solution such as this, right, even in the presence of a bounded medium, two perfect conductors placed parallel to each other with some distance d, I can have a solution, right, for electromagnetic fields that is the same as the values of electric and magnetic fields as represented by a plane wave in an unbounded medium, right. So this is the most common mode of transmission in transmission lines, right. So in the very beginning of this course, we took a look at an example of a transmission line, which was the coaxial cable. I have here an example of a very specific kind of coaxial cable, which has a characteristic impedance of 50 ohms. If you remember, we had a slide that looked at the cross section of this cable, but nevertheless, you can take one of these cables and observe that there is a central conductor and a ground conductor, and these two conductors are separated, right. They are kept parallel or coaxial throughout the length of this cable, right. So we have two pieces of conductors, and we notice that the cutoff frequency for this particular mode is at 0 hertz. Okay, why do I say that? Because f, we said, was m v over 2d, right. So let's consider a dielectric epsilon 1 mu 1. V essentially is 1 over square root of mu 1 epsilon 1, right, and this case corresponds to m equals 0, right, which means that our cutoff frequency Fc for m equals 0 is 0. Okay, this is to say that I can support DC fields, which makes sense. If I have two conductors, I can certainly hold a potential against them. It would mimic that of a parallel plate capacitor, right. So when we use coaxial cables, the way these electromagnetic fields are actually propagating from one end to the other end of this cable is mostly dominated by the TEM mode, okay, because you would most likely use these cables at very low frequency applications, say for example kilohertz or megahertz, to which this is rated, right. So this coaxial cable is related to operate in the megahertz range, right. So one would actually have to make special cables for higher frequency operations, but even those, if you look at these cables and if you notice that there are two independent conductors, right, that is a signal conductor taking the signal from the source and then a ground or a return conductor bringing current back from the load, then the mode that is actually operating, right, in such transmission line systems is the TEM mode, right. All right. With this precursor, I believe we are ready to go to the rectangular waveguide. Okay. Okay. So in this case, you can picture the rectangular waveguide as essentially parallel plate waveguides, right? Two pairs of them, right? Two pairs of parallel plate waveguide. WG stands for waveguides, right? So this is essentially to bring in some kind of confinement, right? So I would like to localize the fields in one of the lateral dimensions. So remember, in the parallel plate capacitor, the y dimension, right, was not quite considered because it is infinitely extending in that axis, right. So now I want to constrain the fields to not permeate all along the y axis as well, right. So I want to bound the electromagnetic fields in both the transverse dimensions and only have one particular propagation direction, right. So that is how I can actually think of the birth of the rectangular waveguide idea, right. So while the textbook that we are following for this course, right, actually goes through the detailed derivation of arriving at the electromagnetic field solutions inside a rectangular waveguide, I believe that students need to understand that what is more important are some very key ideas, right. So the first of which we discussed yesterday, right, is the idea or concept of mode, right. Okay, as a learning student of engineering electromagnetics, just beginning um, to learn the subject, I believe it's important to focus on the key ideas, right. The second is, what is the pattern for E or H, right, look like for different modes, right. And the last, the concept of cutoff frequencies. Okay. So these are some of the questions that we'll try to answer, right, without laboring through a lot of the mathematics that goes behind it. I would like to keep it to only discussing these key ideas in this course, right. But for those who are really interested in trying to know how to solve for the electromagnetic fields for the rectangular waveguide, can follow the text in terms of the mathematical procedure, right. It should not be anything new. It should be mostly looking at the wave equation for the electric field vector and the magnetic field vectors and trying to solve them with the set boundary conditions, right. So when dealing with rectangular waveguides, we again undergo a change of axes, right. So it is very popular to choose this sort of a coordinate axis, right. In general, a rectangular waveguide, we can say that the side lengths are A and B, where A is greater than B, and I can place this with respect to the coordinate system that I have chosen, such that the longer dimension is along the x-axis and the shorter dimension is along y, and the propagation direction for the electromagnetic field is the z-axis, right. This is a little different from the convention we had for the parallel plate waveguides, where the direction of propagation of the electromagnetic mode was actually in the positive x direction, right. All right. So another thing, while I discussed about the key ideas, students may also wonder if we have these coaxial lines or transmission lines for uh, transporting um, electromagnetic fields or voltages and currents at high frequencies, then what is the advantage of rectangular waveguides? What do they bring? Because as we understand, the waveguide only seems to be imparting something called a cutoff frequency, which limits the range of frequencies I can use it for. What are the key benefits, right? So the benefits to studying the rectangular waveguides, right, is one, it actually has lower loss. Okay. So remember that with the TEM mode being confined in the transmission lines, the central conductor, right, um, as it's carrying currents at very high frequencies, we know about the skin effect that actually pushes these uh, currents closer to the surface, right, of the conductor, and this normally leads to a increase in the resistance seen by the charge carriers, right. So we normally notice that transmission lines based off of two conductors, two independent conductors, has a tendency to show higher losses at higher frequencies, right, due to the skin effect. Whereas the way that electromagnetic fields are transported in a rectangular waveguide, uh, we don't quite rely on the currents and voltages, right. We are actually, in fact, there is only one conductor in a rectangular waveguide. All the walls of the rectangular waveguide constitute only a single conductor, right. So the notion of carrying energy from the source to the load is quite different from the case of the transmission lines, where we could actually think of voltages and currents, right. So it is really not a flow of current from the source to the load, right, but rather the currents and charges, right, free charges, as dictated by the Maxwell's boundary conditions, that are actually keeping the electromagnetic wave sustained, right, and these can have quite different patterns depending on the modes. We'll see that very shortly. So one key benefit is using such rectangular waveguides uh, does provide us with a lower loss, right. And the second is power handling. So again, taking the example of the coaxial line, you remember that the fields are highly concentrated around the central conductor, right, whereas the ground conductor has a much larger circumference, right. So the fields have a lot more surface area to terminate themselves, right, whereas the central conductor, so the electric field concentration gets very large, right, or the intensity of the electric field gets very large close to the central conductor, right, and this can lead to breakdowns in the dielectric that separates the central signal conductor and the ground conductor, right, and is often the source of failure when I am trying to transport very large voltages, right. Again, the sense of large for voltages here should quite simply be uh, understood as that every dielectric material has a certain breakdown electric field, and if I were to apply a certain voltage that causes the field strength to get close to this breakdown field, I can see that the dielectric material can fail and start to conduct currents, right. So, in the case of rectangular waveguides, we can actually handle very high powers, right, which is why we see these very often either at the transmit side of your 5G and 4G base stations, and also in satellites, right, when we have the satellite transmitting some information to the ground station, the transmit side of the satellite would actually use rectangular waveguides in order to transport power or handle the electromagnetic fields. In fact, you can also play with the material that's within the rectangular waveguide, right. By pressurizing it with air, you can actually improve the power handling also further. Okay. So, without going through the derivations for the electric and magnetic fields, I borrow from the textbook the expressions for the electric and magnetic fields, the full three-dimensional field, right, the vector field solved for the TE case and the TM case, right. So, even for the rectangular waveguide, I have two scenarios, the transverse electric and the transverse magnetic, right, and we said that this can have a meaning with respect to the waveguides, where we say that if the electric field along the propagation direction, which now is the z direction, right, if the electric field along the field direction is 0 at all points within the waveguide, we call that or classify them as TE modes, right. And similarly, if the magnetic field along the propagation direction is 0, we call them TM modes, right. So, we have such a classification as opposed to the classification we had when we dealt with plane waves interacting with a dielectric boundary, where we defined a plane of incidence and we had the electric and magnetic field vectors in relation to the plane of incidence. Okay. Now, you can see that there is a fairly involved expression, right, but it should be no surprise that in the parallel plate capacitor we saw a transverse resonance condition which led to standing waves, right, in the region between the parallel plates. We are seeing the same scenario here too, right. So, I am seeing one standing wave pattern along the x dimension, right, and then we have another standing wave pattern along the y dimension. So, the x and y dimensions are the bounded dimensions by the conductor, and then the z dimension is the propagation direction, right. So, now the spatial variation of my magnetic field is composed of standing waves created in the x and y dimensions and a propagation wave in the z dimension, right. So, a couple of things that we can sort of infer from these expressions, right. So, I have used the term kx square plus ky squared, right. So, in general we can say that the k vector in this scenario, right, will have all three components, right, and that the component kz is the contribution to the phase of the propagating wave, right, or the propagating mode. So, we also know the Pythagorean relation, right, that relates the magnitude of the k vector is kx squared plus ky squared plus kz squared, right. This condition still holds good, right. So, in this case kx, right, is m pi by a right? So if you can go back, the expression for the fields reflecting the plane wave reflecting off of a perfect conductor, we saw that the electric field, the net electric field, right, had standing waves in the z direction, right? And this was indicative of the sine kziz or the cosine kziz in the expression, right? So the prefix to the dimension x, right, is what we assign as kx, right? So here kx is m pi by a and ky is n pi by b. Okay, so kx square plus ky square is essentially m pi by a whole square plus n pi by b whole square, right? Remember these for a given mode, right, which can be identified by the integers m and n, right? And if I have the dimensions of the rectangular waveguide, I can actually estimate what kx and ky are, right? So remember the mode electric and magnetic field expressions that you see on the left is the comprehensive list for all the modes under that category, right? So we can say that this TE, right, requires a certain subscript, right, to say which mode we are talking about, right? So remember m and n are integers and I can choose numbers 0, 1, 2, 3 for m and n can go from 0, 1, 2 or 3, right? So in the case of the parallel plate waveguide, we just required one integer. In this case, we require two integers to establish how many half cycles of the sinusoid are present in each of the x and y dimensions, right? So m signifies the number of half cycles that are present in the x dimension, and n indicates the number of half cycles in the y dimension. Okay. So let us ask the question, what are some allowed values of m and n, right? Because remember that when we looked at the TE case for the parallel plate waveguide, when we put m equals 0, we actually didn't get a solution, we just got 0 fields, right? So let us see if can we put m and n both to be 0 in this case, right? So it seems like hz is okay because it's only a cosine of 0 and cosine of 0. So hz can be a constant, but we notice that ex and ey becomes 0, right? So there's either a sine n pi by y or a sine m pi x by a, right? And both of these sine terms would go to 0 if both m and n were 0, right? So which means that there's no electric field at all, right? So there cannot be an electromagnetic wave, which means to say that TE00 does not exist. Okay. But you can notice that other index pairs, right, of TE01 or TE10 or TE11 and all other higher numbers. So one of m or n has to be a non-zero element, right? Only then do we see that there is a consistent electromagnetic field, right, a vector field that I can establish in the waveguide. Okay, so now with Tm, we also need a subscript here, Mn, right? But the expressions look a bit different naturally, right? Because in this case, Hz is 0, right? So there is electric field in the propagation direction, but no magnetic field in the propagation direction. We look to see a very similar form. The kx and ky values are the same as we saw in the TE case. So in this case, it's quite easy to see that if I put both m and n to be 0, here also I will not get a valid vector field for the electromagnetic wave. So TM00 also doesn't exist. Okay. So this is to say that I cannot have a plane wave equivalent solution like we did for the parallel plate waveguide of a plane wave going at grazing incidence, right, satisfying the boundary conditions. I cannot have such a solution for a rectangular waveguide. The moment I cap the with parallel plate waveguides in both x and y, right, I no longer can have the TEM mode, right. So this is also to say that TEM mode does not exist for the rectangular waveguide. And since here the electric field is dependent on the sign function for both the kxx and kyy, we also find that TM01 and TM10 does not exist, and the lowest count for m and n has to be 1 each, right. So TM11 is the first allowed mode, right, or the first allowed solution with the least number of half cycles, right.